To conclude, we will discuss object-oriented data models. These are typically represented using the Unified Modeling Language, or UML. As the term suggests, this is essentially an OO system modeling notation, which not only focuses on data requirements, but also on process modeling. It was accepted in 1997 as a standard by the Object Management Group, or OMG, and approved as an ISO standard in 2005. The most recent version is UML 2.5, introduced in 2015. To model both the data and process aspects of an information system, UML foresees various diagrams, such as use case diagrams, sequence diagrams, package diagrams, deployment diagrams, etc. From a database modeling perspective, the class diagram is the most important. It allows to visualize both classes and their associations. Before we discuss this into more detail, let's first provide a recap of object orientation. Two important building blocks of OO are classes and objects. A class is a blueprint definition for a set of objects. Vice versa, an object is an instance of a class. In other words, a class in OO corresponds to an entity type in ER and an object to an entity. You can think of an example class student and an example object student Bart. Each object is characterized by both variables and methods. For our student objects, example variables could be the student's name, gender, and birth date. Example methods could be calc_age, which calculates the age of a student based upon the birth date, isBirthday to verify if the student's birthday is today, isPassed course ID, which verifies if the student is passed for the course represented by the course ID parameter, etc. Information hiding or encapsulation states that the variables of an object can only be accessed through either getter or setter methods. A getter method allows to retrieve the value of a variable, whereas a setter method allows to set it. The idea is to provide a protective shield around the object to make sure that values are always correctly retrieved or modified. Similar to the EER model, also inheritance is supported. A superclass can have one or more subclasses, which inherit both the variables and methods from the superclass. As an example, student and professor can be a subclass of the person superclass. In object orientation, method overloading is also supported. This implies that various methods in the same class can have the same name, but a different number or type of input arguments. Here you can see an example class supplier. In UML, a class is represented as a rectangle with 3 sections. In the upper part, the name of the class is mentioned. In the middle part, the variables, and in the bottom part, the methods. Example variables we have here are supplier number, supplier name, etc. Example methods are the getter and setter methods for each of the variables. Note that UML also allows to define access modifiers for each of the variables and methods. An access modifier specifies who can have access to the variable or method. Example choices are private, in case the variable or method can only be accessed by the class itself, public, in case the variable or method can be accessed by any other class, and protected, in case the variable or method can be accessed by both the class and its subclasses. To enforce the concept of information hiding, it is recommended to declare all variables as private and access them using getter and setter methods. In our example, you can also see two objects, supplier 1 and supplier 2, which have been created from the class supplier. Both have values for their variables, as you can see illustrated. Analogous to relationship types in the R model, classes can be related using association types. Multiple associations can be defined between the same classes. Also, unary or reflexive associations are possible, where a class engages into a relationship with itself. Associations can be further augmented with direction reading arrows, which specify the direction of querying or navigating through it. In a unidirectional association, there's only one way of navigating as indicated by the arrow, whereas in a bidirectional association, both directions are possible and hence there is no arrow. Here you can see a table listing the similarities between both the UML and EER model. As already mentioned, a class corresponds to an entity type, an object to an entity, and a variable to an attribute type. There is no EER counterpart of a method. An association corresponds to a relationship type and a link to a relation. The multiplicity refers to the EER cardinality, and you can see the four options compared, whereby the asterisk or star is introduced to denote a maximum cardinality of n. Here you can see an example of a unidirectional association between the classes supplier and purchase order. It implies that all purchase orders will be retrieved through a supplier object. Hence, according to this model, it is not possible to navigate from a purchase order object to a supplier order object. Also note the multiplicity of the association, which corresponds to the cardinality of the EER relationship type. Here you can see an example of a bidirectional association between the classes supplier and product. According to this UML model, we can navigate both from supplier to product as well as from product to supplier. Note that, similar to the ER model, the association is also characterized by the variables purchase price and delivery period. A qualified association is a special type of association. More specifically, it uses a qualifier to further refine the association. The qualifier specifies one or more variables that are used as index key for navigating from the qualified class to the target class. It allows to reduce the multiplicity of the association because of this extra key. Here you can see an example. We have two classes, team and player. They are connected using a 1 to n relationship type in the R model, since a team can have 0 to n players and a player is always related to exactly one team. This can be represented in UML using a qualified association by including the position variable as the index key or qualifier. A team at a given position has 0 to 1 players, whereas a player always belongs to exactly one team. Qualified associations can be used to represent weak entity types. Here, you can see our earlier example of room as a weak entity type being existent dependent from hotel. In the UML model, we can define room number as a qualifier or index key. In other words, a hotel combined with a given room number corresponds to 0 or 1 rooms, whereas a room always belongs to one hotel. Similar to the EER model, UML also allows to model specialization or generalization relationships. Here you can see our earlier example with artist, singer, and actor. Note the hollow triangle which represents a specialization in UML. The specialization characteristics, such as total, partial, or disjoint overlap, can be added next to the triangle. UML also supports multiple inheritance. Two types of aggregation are possible in UML: shared aggregation and composite aggregation. In shared aggregation, the part object can simultaneously belong to multiple composite objects. In other words, the maximum multiplicity at the composite side is undetermined. The part object can also occur without belonging to a composite object. A shared aggregation thus represents a rather loose coupling between both classes. In composite aggregation or composition, the part object can only belong to one composite. The maximum multiplicity at the composite side is 1. This represents a tight coupling between both classes, and the part object will be automatically removed when the composite object is removed. Here you can see two examples. A shared aggregation is indicated by a hollow diamond and a composite aggregation by a filled diamond. We have a shared aggregation between company and consultant. A consultant can work for multiple companies. When a company is removed, any consultants that worked for it remain in the database. We have a composite aggregation between bank and account. An account is tightly coupled to one bank only. When the bank is removed, all connected account objects disappear as well. Here you can see our earlier HR example in UML notation. Note the various variables and methods for each of the classes. We also included a shared aggregation between department and location and between project and location. We have two unidirectional associations between employee and project and between department and project. UML offers various advanced modeling concepts which allow to further add semantics to our data model. The changeability property specifies the type of operations which are allowed on either variable values or links. Three common choices are default, which allows any type of edit, add only, which only allows additional values or links to be added, so no deletions, and frozen, which allows no further changes once the value or link is established. You can see this illustrated here. The supplier and purchase order number are both declared as frozen, which means that once a value has been assigned to any of them, it can no longer change. The languages variable of the supplier class defines a set of languages a supplier can understand. It is defined as add only since languages can only be added and not removed from it. Also, note the add only characteristic added to the on order association. It specifies that for a given supplier, purchase orders can only be added and not removed. The Object Constraint Language, or OCL, which is also part of the UML standard, allows to specify various types of constraints. The OCL constraints are defined in a declarative way. They specify what must be true, but not how this should be accomplished. In other words, no control flow is provided. They can be used for various purposes, such as to specify invariants for classes, to specify pre and post conditions for methods, to navigate between classes, or to define constraints on operations. Let's provide some more detail. A class invariant is a constraint which holds for all objects of a class. An example could be a constraint specifying that the supplier status of each supplier object should be bigger than 100. Pre- and post conditions on methods must be true when a method either begins or ends. As an example, before the method withdrawal can be executed, the balance must be positive. After it has been executed, the balance must still be positive. OCL also allows to define more complex constraints. Here, you can see our two classes, employee and department. They are connected with two associations to define which employee works in what department and which employee manages what department. Note the role names which have been added to both associations. Various constraints can now be added. A first constraint states that a manager of a department should be at least 10 years employed. The context of this constraint is the department class. The constraint applies to every department object, hence the keyword invariant. It then becomes self.managedby.years employed strictly bigger than 10. We use the keyword self to refer to an object of the department class. We then use the role name managed by to navigate to the employee class and retrieve the years employed variable. A second constraint states a department should have at least 20 employees. The context is again department, and the OCL constraint becomes self.workers size bigger than 20. Note that self.workers returns the set of employees working in a specific department. The size method is then used to calculate the amount of members in the set. A final constraint says a manager of a department must also work in a department. In OCL, this becomes self.managedby.worksin equals self. From these examples, it is clear that OCL is a very powerful language which allows to add a lot of semantics to our data model. For more details on OCL, we refer to www.omg.org/OCL. Dependency is another interesting UML concept. It basically defines a using relationship which states that a change in the specification of a thing may affect another thing that uses it. It is denoted by a dashed line in the UML diagram. An example could be when an object of one class uses an object of another class in its methods, but the referred object is not stored in any variable. Let's illustrate this with an example. We have two classes, employee and course. Let's say an employee can follow courses as part of a company education program. The employee class includes a method toCourse which determines whether an employee followed a particular course represented by the input variable CNumber. Hence, an employee object makes use of a course object in one of its methods. This explains the dependency between both classes. We hereby conclude the discussion of the UML class diagram. We can now conclude the chapter. We started by reviewing the basic concepts of data modeling. This was followed by in-depth discussions of the hierarchical, codicil, entity relationship, enhanced entity relationship, relational, and unified modeling language models. Many of the concepts introduced will be discussed further in subsequent chapters.